All right, welcome to another calculus lecture. In the last lecture, I said that the next lecture would be about computing derivatives and how to apply or we'd learn about various rules for computing these things so we didn't have to do the limit definition each time. But before getting to that, I think it's actually a little bit more natural to talk about a few different aspects of how we interpret the derivative. So I want to do a few more graphical aspects of the derivative, as well as introduce some other notation for the derivative and talk more about the derivative as a rate of change. So first thing I want to talk about is differentiability. So the property of being differentiable. As smoothness. And let's go ahead and get a coordinate axis out here. Nice big one. So if I have a function which looks something like this, then the idea is that at these points, and maybe we'll call this point A and this point B. So differentiability, so the property of being differentiable, means that we have a well-defined tangent line. So we noted before that if that the derivative of a function represents the slope of the tangent line at that point. And so if a function is differentiable, I can construct a tangent line. That's what that means. Well, if I look at the graph right here, maybe at the point A, notice what happens. As I approach along the left, what does my tangent line look like? Well, it looks like about the slope of this part on the left. So it looks like a line with this slope. So something like that. But if I approach on the right, look at what the slope looks like. It's not this, but rather something like this. And similarly, we can argue the same thing for this other point. Where if we draw the tangent lines on each side, or at least what we would expect the tangent line to be if we were approaching from either the left or right, these tangent lines don't agree. They are clearly not the same line. However, if I were to draw the tangent line at a smooth point, well, then there's no problem. The tangent line exists, and it makes perfect sense to sort of look at it and think about it as an actual object. So when a function fails to be differentiable, what it means for the graph is that the graph is going to exhibit some sort of behavior where the tangent lines from the left and right do not agree. So let's write that down. So if a function fails to be differentiable at a point, x equals a maybe, then the graph of f of x will have some sort of sharp point, and the formal word for this is actually a cusp. That is, the function isn't some smooth point, I had to sort of, as I was drawing this graph, I didn't just smoothly move my pen around, I actually abruptly changed the direction that I was moving my pen. And this represents abruptly changing the slope of the tangent line. And so, if a function fails to be differentiable, then its graph is going to have something like this occurring, and vice versa. So vice versa, vice versa, I don't actually know how you spell that. Vice versa, a cusp in a graph means that f of x is not differentiable. And so this works both ways. If a function fails to be differentiable, a graph is going to exhibit some sort of strange behavior at that point, and vice versa. If a graph has some point where you have a cusp or a sharp edge like this, or even a discontinuity, then you're going to fail to be differentiable at that point. So the idea is that differentiability is some measure, this is an if and only if, or an equivalency, so it's supposed to be an arrow with two little lines in between it, a double-sided arrow. So differentiability is really the same thing as smoothness. And I'll put this in quotation marks because I haven't rigorously defined what smoothness of a graph is, but I think at least intuitively it should be obvious what we mean by a smooth graph and a sharp point in the graph. Okay, so that's differentiability as smoothness. The next thing that I want to talk about, and I don't actually have room for it on this page, is, so we've measured smoothness with the derivative. We can also measure steepness. So the derivative as steepness. And here again, we'll go ahead and get a coordinate axis. And let's go ahead and get a generic function in here, and we'll make it a simple one. So maybe something with this shape. And I want to draw the tangent line at a particular point. So maybe let's use blue for this. And so the tangent line should look, well, roughly like this. Doesn't have to be exact. So this is going to be my tangent line, t of x, and I'm going to just say that it's equal to mx plus b for some numbers m and b. I don't know what they are. I haven't rigorously said what my function f of x is, but if I did, then we could compute these things, and we'll show how to do that a few lectures from now. But if I just say that my function is this, and I say that my tangent line is this, I want to somehow quantify the derivative in regards to this slope. So this is line tangent to f of x at x equals a. And so what, if I look at this function, what is this slope really measuring? If I were to draw another line, a tangent line up here, then you can see that it's really sort of measuring the steepness of the graph. As the sort of the slope of the tangent line is more shallow, it's closer to 0, the slope of the function is smaller. It's sort of more shallow, but as we increase and make the function steeper, so too does the slope of the tangent line change. And so if I pick out some points here, so let's pick out a point, maybe A, capital A and capital B, then what I want to say is that f prime of A, so if I think about what the slope of the tangent line would be right here, or what the derivative is at this point, then f prime of A is going to be, you know, it would look something like that, and then this one would be something like this. The slope of this line is less than the slope of this line. This is a positive slope, it's tending upwards, and this one is tending downwards. So this is going to be less than, what's the slope of this tangent line? It's m. And then the slope of this tangent line, it's this point right here is steeper than at A. And so the tangent line, the slope of the tangent line, is going to be smaller than the derivative at B. So is less than f prime of B. Okay, and so the idea here, the derivative it sort of quantifies the steepness of a graph. And in your homework, I have you, in one of the online quizzes, I have you sort of look at one of these graphs and say, okay, well, if I have a point and I have a tangent line at that point, what does the derivative look like at points around that? And the goal is to perform a similar analysis as this, to say, okay, well, the slope of the tangent line over here, which is the derivative, is going to be smaller than the slope of this tangent line, and that in turn is going to be smaller than the slope of this tangent line. And of course we have that f prime of little a is equal to m, because the derivative and the slope of the tangent line at this point A, where the tangent line is constructed, these certainly agree. Okay, so that's all I wanted to say about that. Again, the idea is that the derivative quantifies steepness, and we can say that a graph is more or less steep by saying that its derivative is larger or smaller in particular places. So a graph is steeper if its derivative is large, and vice versa. So a graph is steeper if its derivative is large, and if the derivative is large, you're going to have a steeper graph, and a graph is more shallow. Likewise, a graph is more shallow if the derivative is small, and vice versa. Okay, so the derivative allows us to quantify the steepness of a graph, steepness or shallowness, however you'd like to sort of say that. All right, the next thing that I want to talk about is some alternative notation for the derivative. Notation for the derivative. And this is Leibniz notation. So the notation with an F and then a prime on it is Newton's notation, and the notation that I'm about to write down is Leibniz notation. So if y is a variable which is a function depending on x, so all this is saying is that y is a function of x, then f prime of x is also denoted by this quantity dy divided by dx. So again, we're not saying anything new here, we're just introducing a new way of writing the derivative. And in some contexts, it's better to use this notation because this notation reflects the idea that the derivative is a rate of change, or a slope, which these two things being the same thing. And namely, the rate of change is, so f prime of x is units of y per unit of x. If x changes by 1 unit, then y changes by dy over dx units. And this is precisely what the slope of a line is. If I have a line that is 5x plus 1, then the 5 there says that for every one value I increment x, the value y is going to change by 5. I'm going to add 5 to the value of y. And so Leibniz notation is convenient in that it allows us to think about the derivative really as what it represents. It's a rate of change. The prime notation, the Newton notation, is a little bit more expedient when you're doing calculations, but the dy dx really conveys this idea that the derivative is a rate of change. And it also suggests what the units for f prime of x are. It tells you that it is units of y per unit of x. Okay, so let's maybe do an example with thinking through what this sort of looks like. So example. So if P of D represents the number of pounds of sugar produced by some factory when the price per pound is D dollars, what are the units and meaning of P prime of 3 equals 50? So if I told you that P of D represents the number of pounds of sugar I produce when the cost to produce a pound of sugar is D dollars, what exactly does this P prime of 3 equals 50? What does that statement mean? And also, what are the units of P prime of 3, or just P prime in general? Well, the units are fairly easy to think about. So the units are, well, what does the Leibniz notation tell us? It tells us that it is number of pounds produced, so pounds produced per dollar. D is in dollar, so per dollar. Or we could have just said pounds per dollar. And this really is one of the nice things about the Leibniz notation, is it informs our intuition immediately of what the units are for a derivative. It is a dependent unit, the number of dependent units per independent unit. So everything here is depending on dollars. So these are what the units are. And now we need to think about what is the meaning of p prime of 3 equals 50. Well, what have we said before that the derivative represents? So recall that the derivative represents the instantaneous rate of change. And so, when the price per pound is $3, that's what this 3 here means. Our price per pound is $3. Price to produce a pound is $3. The number of pounds being produced well, that number is changing at a rate of 50 pounds per dollar. And there's yet another way that we can say this, said differently. If we change the price by $1, or if the price changes by $1, then the number of pounds is going to also change by $1. The number of pounds, not by $1, it will change by 50 pounds. Produced will change by 50. And so if I increase the dollar, or if I increase the price per pound by $1, then I am going to increase the number of pounds produced by $50. And likewise, if I decrease the price per pound by $1, then I'm going to decrease the number of pounds produced by 50. And as I say this out loud, I realize that this should be negative. So if I increase the price, I decrease the amount. But anyways, the example is written, and so that's what we're just going to stick with. Okay. And this is another way of thinking about the derivative, is it informs you, if I tell you that a derivative at a particular point has a particular value, then it's telling you that if I change that input by a little bit, maybe by 1, how much is the output going to change by? Okay, and this is precisely what a slope means. And slopes of tangent lines, instantaneous rates of change, derivative, these are all really just different ways of conveying the same property of a function. So maybe we'll conclude by noting that. So instantaneous rate of change this is the slope of the tangent line. And this is the derivative. And so one of the really nice things about calculus is we can take something like a graphical idea, the slope of a tangent line. I can relate it to a derivative, which is a purely analytic object. I just compute a limit, which is I do this algebraically or by whatever means I want to. And I can also relate that to something very concrete in the real world. I can relate it to how fast a quantity is changing. If I change the input by a little bit, how is the output affected? And that's really the power of calculus, is to be able to relate all of these concepts and view the same thing in all of these different ways and through these different lenses. Okay, so that's everything I wanted to talk about with interpreting the derivative. Next week we will begin by doing a lot of the derivative rules, and a large portion of it is actually going to be spent just writing down what those rules are. I'm not going to prove any of them, but I'll write them down, and then that will allow us to compute derivatives much faster rather than having to do a limiting process every time and computing a limit each time, because that is honestly hell after you do it a few thousand times. Or even just 10 times. I've computed a lot of limits in my life. I don't want to talk about it. Anyways, I will see you all for next week's lectures.